related to wellbore stability. Let's imagine that we have a vertical wellbore that is being drilled into conditions in which this is the maximum stress in the plane perpendicular to the wellbore, and this is the minimum principal stress in the plane perpendicular to the wellbore. With Kirch's equations, as you already did, you can calculate what is the hoop stress, right? The hoop stress is going to depend on the angle with respect to that maximum principal stress, sigma 1. And there are going to be 2 points which are going to be points that we're going to be very interested in, because those are the points in which we have quite different stresses. The first one, it's a point like over here. Let's call it point number 1. In that point, you have a lot of accumulation of compressive stress, because your compressive stresses are deviating in order to go through to the wellbore. Everything that was going through the wellbore before now has to go through the sides, and because of that, you're going to have a lot of compression in this location. The hoop stress at that location is going to be given by this equation, where this is the pressure in the wellbore plus 3 times sigma 1 minus sigma 2. And when we consider changes of temperature, there's going to be an additional component, which is going to be the change of hoop stress due to thermal changes. So, do you think it's going to be good or bad to have to drill with a cold fluid in this wellbore for that point over there? Why would it be bad? So when you drill the wellbore, you immediately after you pass through here, you put a lot of compression in this direction, in the rock. And then now your wellbore is circulating and cooling the rock.
Cooling the rock increases compression.
Okay, so I think we could say it's going to be good, okay? Because you're going to lower the compression. If you were about to fail the rock because there was too much compression, now you're going to lower that compression. So in something that we're going to see later on, actually I'm writing right now the chapter on wellbore stability, something that you're going to need later on, but you're going to have to go mostly on your own through that. We're going to see that when we have lots of compression in one direction and not much compression in the other direction, here we're going to have shear failure. And that shear failure causes something which are called breakouts. So in order to avoid breakouts in the wellbore or shear failure around the wellbore, that change of temperature actually is not going to be bad, because it's going to decrease that compression in that direction. But also you can calculate the hoop stress at this location. And at that location, the equation for that is going to be similar to the one above, but with a different coefficient in front of those principal stresses. And notice that now here we have, this one is larger than that one, right? So now we have more compression here in the breakouts. Now this one goes with a negative sign. This is the maximum stress, and this is the minimum. So by having that combination, already here you're going to have, you may have even a tension in that location, in this direction. And if you circulate a cold fluid, you're going to have even more tension, right? And more tension, in this case, it can cause tensile fractures in this location. And it happens that sometimes you can be drilling a wellbore and everything is fine, but once the rock starts to cool down, even maintaining the same mud pressure, the wellbore may fail because you're favoring the initiation and the propagation of some of these tensile fractures. So this solution is the steady state solution. You could also solve this problem if you do it unsteady state, and you can solve the heat equation that you saw before, and you could do that, solve that as a function of time, see how hoop stress changes as a function of time. But if you're going to take a shortcut, similarly to the equation that we derived for change of lateral stress as a function of temperature for the 1D strain case, for the wellbore case with cylindrical geometry, this is going to be your result. All right, guys. I think we're going to end here with thermo-elasticity, and on Thursday we're going to talk about viscoelasticity very quickly, and about a topic I like a lot, which is called chemoelasticity, and that's going to be the end of all of these couple processes, and then we'll start talking about plasticity. Okay? All right. Okay, guys. Thank you. See you on Thursday.